Howdy, everyone, and welcome to the first of hopefully many enjoyable lectures about astronomy, ASTR 103, for the fall of 2022. Today, I'm going to be essentially giving an overview of science and astronomy in general. I'm going to be splitting this lecture into two parts because previous experience, I tend to ramble on so much that these lectures tend to get a little long. So the beginning, we're going to be talking about essentially not tools, but the scientific notation, the terminology that science uses. And then the next part will be about the scientific method itself. So without further ado, I always get this wrong. I always can't tech right. There we go. So the overview is that astronomy is a modern quantitative science that studies the universe. So astronomy basically deals with everything that deals with everything aside from the Earth, but that's in fact not true. We do in fact deal with the Earth, just not as, specifically as biologists or geologists. Astronomy is arguably one of the oldest sciences in existence. The mathematics obviously predates astronomy, but from a point of view of understanding the universe around us, documenting such an understanding, astronomy really can be argued that it is the oldest science because it deals with practical matters for the people at that time. Specifically, astronomy was used in terms of calendar keeping. The first calendars were based on the moon, the movement of the moon, or the movement of the sun. And these calendars were vital not only for religious holidays or spiritual reasons, but also because of agricultural reasons. People needed to know when to plant, when to harvest, that sort of thing. So astronomy has been used for essentially ever since humanity has been civilized, shall we say, has organized itself in a agricultural way. We'll also talk about scientific notation and orders of magnitude, particularly because astronomy is fascinating to me because it is a science that has, in my opinion, the largest range of sizes and long range of sizes from spatial scales to temporal scales of any other science, meaning that we deal with the smallest atomic size objects all the way out to the entire size of the universe. No other science looks at sizes with that such a range. And we're going to be looking at ultimately these orders of magnitude and how and what physical phenomenon that astronomers are interested in fit into those particular orders. And then, as I said, the next lecture, we're going to be talking about the scientific method, essentially what it is, what it isn't, and how it can be used to distinguish actual scientific endeavor versus pseudoscience. The best example, or the archetypical example, is what distinguishes astronomy from astrology. So as I said, astronomy is one of the oldest, if not the oldest science that we know of. And we have evidence of this in terms of observatories. And what I mean by observatories, particularly the early ones, there's something of a stretch for that term. But for example, there is this mound that we see, the upper photo, is in Newgrange, Ireland. And as an observatory, it's fairly simple. What it is you go down this hall, as it were, and you go into the central chamber. That central chamber is in complete darkness until one moment over the course of the year, the sunrise on the summer solstice. The position of the sun at that time is such the light streams directly down that hallway and illuminates that chamber. The significance of why they built it that way is unknown, but It is a observatory in the sense that it is it was specifically designed to illustrate a particular celestial event. In this case, the position of the sun at summer solstice. And there are other examples of observatories such as this from the from Stonehenge to the Mayans to the Babylonians and so forth that have survived over the years. These days, observatories are far more technical, far more sophisticated. The one on the bottom right is the VLA, or the Very Large Array, a staple of radio astronomy. And we'll learn all about that, all about those particular instruments later on in the course. But all of these instruments, the simple one in Newgrange, the VLA, all the way up to the JWST, which has recently been launched, all of these serve to help us understand how the universe works, how the celestial bodies move, how they came into being, how they evolve, and ultimately how they end. And in so doing, trying to find our place within that vast reality. So as I said, what is astronomy? As I've said, it is the study of the universe, great and small, from the beginning, from the point of creation or from the Big Bang to however it's going to end at the end, or well, at the end of time. And so we're going to be talking about things such as, atoms. We're going to be talking about light, moons, planets, galaxies, superclusters, and so forth and so on. Now, when dealing with astronomy is a quantitative science, as many sciences are. And in order to quantify things, you need to have numbers. Now, in this class is not a math-heavy course. I will be going over equations, but really the equations are there to guide your understanding of relationships, how one thing is related to another. For example, when we talk about the force of gravity is inversely related to the distance squared, but directly related to the mass. So the equations serve as guideposts for your understanding of relationships of one quantity to the other. But I am going to be showing you a whole bunch of numbers. And in order for those numbers to make sense, we kind of have to go over scientific notation. Now, scientific notation is a way of writing numbers that are very, very large or very, very small. I would almost say incomprehensibly large or incomprehensibly small. And again, we're talking about size scales that are on the order of subatomic or the size scales of galaxies and beyond. So in this simple form, if you're going to write a number in a scientific notation, in its simplest form, it is A times 10 raised to the B power. When you write it this way, an appropriate way to write the scientific notation is that A is a number between 1 and 10. Now, it's not an integer. It's a real number. It's not an integer. So you can write 1.2 or 3.7 or 3.789 and so forth, so long as it's a number between 1 and 10. You don't want to write, say, 12 times 10 to the what have you. And now B is an integer. So while A was a real number, B is an integer. So you would have 10 to the 8th or 10 to the 9th or 10 to the negative 3rd, for example. So a positive exponent, like 10 to the 3rd, means that the decimal place moves over to the right. A negative exponent means that the decimal place moves over to the left. Now, what do I mean by moving the decimal place? Let's take an example of 450. The decimal place is right after the 0, on the right-hand side of the 0. If we were to write this in scientific notation, what we would do is we want to move that decimal so that only one number is on the left-hand side of it. So here we're going to move it once to get behind the 5 and then one more time to get behind the 4. That in scientific notation is 4.5 times 10 to the second, because we moved the decimal place twice in order to get there. Now let's take the number 0.045. In this case, we're going to move the decimal over to the right. Again, we're going to be doing this such that the decimal is on the right-hand side of the first integer. In this case, you go you move 1 to get behind the 0, and then you move another time to get behind the 4. So again, we have 4.5, but in this case, it's 4.5 times 10 to the negative 2, because we've moved the decimal point over to the right. This can be used to express any number, no matter how large or how big or how small. One of the most important things in science, in any science, and when I was teaching laboratories, astronomy or physics laboratories, I would emphasize this to no end, and that is units. One of the reasons, if you remember, Hubble was, when it was launched, it was nearsighted, I think. It was out of focus. One of the reasons for that was because the units were not the units from one group to the next. When the data from, or the schematics from one group moved to the next, the units weren't properly taken into account. One of the British, or one of the UK satellites, the Beagle, if I remember correctly, also failed to actually hit the planet. It missed Mars entirely because, again, of poor unit conversion. So units are very important. Now, what is a unit? A unit is a measure of something. It could be distance, it could be time, it could be weight, or rather, it could be mass, things of that nature. In this class, we're going to be using what is known as the MKS system, or SI system. And what that stands for is MKS is meters, kilometers, and seconds. Or excuse me, meters, kilograms, and seconds. So of those three, the three fundamental quantities of distance, mass, and time, the default unit is a meter, is a kilogram, and it is a second. So for example, if we get a number that is 2,050 meters, we want to first put that into scientific notation. So we want to get that decimal over to the left behind the 2. We do that by moving it 3 times. So the number becomes 2.05 times 10 to the 3rd meters. But to standardize it, we then will do a unit conversion, or essentially to get it into kilometers. There are 1,000 kilometers, or 1 times 10 to the 3rd kilometers, or meters, in 1 kilometer. So there are 1,000 meters in 1 kilometer, or 10 to the 3rd meters in 1 kilometer. And so you can convert that from 2.05 times 10 to the 3rd meters to 2.05 kilometers. This way, the idea here is not only to keep things consistent, but also to try to keep things as compact and as simple as possible. When we think of, when we hear the word kilometer, what we're seeing is we're here and we have the unit, meter, and then we're tacking on a prefix. And each of these prefix refers to essentially an order of magnitude. And if you are working, if you've worked with computers, and a number of these are, and really just if you buy computers, a lot of these are probably very familiar, particularly mega and giga. So let's keep with meters. The base unit is meter, and then you get to kilometer, which means it's 1,000 meters. You get to megameter, which is a million meters. You get to gigameters, which is a billion meters, and so forth. So, or a kilogram, a megagram, a gigagram would also be it. Then you get down to, if you go the other direction, you get centimeters, which are 100. There are 100 centimeters in 1 meter. Then a millimeter, 1,000 millimeter, 1,000 millimeters in a meter, and then micrometers, and so forth and so on. There are prefixes above and below, but that really goes beyond the scope of what we're going to be talking about. 1 second, I need to close something out here. All right. So what I've used the term orders of magnitude. And what does that mean? An order of magnitude are a range of numbers within a power of 10. So for example, the numbers 1, 2, 3, 4, 5, 6, 7, 8, and 10, 8, 9, and 10 are all within one order of magnitude. The numbers 11 all the way up to 100 are also an order of magnitude, and so forth and so on. When astronomers really, when we talk about an order of magnitude, we're really kind of guesstimating things. Like, for example, the sun is about 50. The surface temperature of the sun is about 55,000 Kelvin within an order of magnitude. We actually know it much better than that. But an order of magnitude, basically, when you hear the term order of magnitude, that's really just a range or a guess of how far, give or take, or how close a number, give or take, is to reality. So when we, and more to the point, it's a way of estimating things. So for example, you have, let's say you have 780, and you want to know what order of magnitude that is. What you do is you'd round up to 1,000. 1,000 is 10 to the third, so it's in the third order of magnitude. 8.9 times 10 to the sixth, or 10 times 10 to the sixth, that's 7 orders of magnitude, and so forth. So for example, if something were of a size of 10 to the 7 meters, and you were comparing it to something that was of the size 10 to the third meters, and what you're saying is that the first object is 4 orders of magnitude larger than the second. So instead of doing the actual math, you can make a quick estimate as to how much larger one thing is to the other. Distance and time in the universe. As I said, astronomy is almost unique in the fact that we deal with the smallest distances and the largest distances of any other science. And in terms of time, when you talk about the age of the universe, you're talking about billions of years old. So it is sort of a staple of astronomy that we're going to be dealing with times and distances that are inconceivable. We can understand them from an intellectual point of view, but really to conceptualize that we are in a universe which is 19 billion light years across, or 95 billion light years across. For me, that's just almost it is inconceivable to think of a distance that way. Even the distance between the Earth and the sun, which is 149 million kilometers. I can't imagine what 149 million is in reality. I can barely conceptualize what 149 kilometers is. So, first question. A parsec is a measure of time. Give you a few moments for that. A parsec, is it a measure of time? Answer is no. Han Solo's statement, no matter how you try to twist it, doesn't make any sense. Doing the Kessel run in 12 parsecs, that doesn't make any sense. A parsec is a unit of length. And when we talk about, speaking of parsec, one of the things that we do in astronomy is, as I mentioned, we have a base unit system, which is meters, kilograms, and seconds. But we often come up with additional terms, because if we stick with meters, then we will then become, if we stick to meters and then we'll talk about distances out to stars, the numbers become ridiculously large. So the distance between the Earth and the sun is 149, as I said, 149 million kilometers. And that's just to the sun. To Alpha Centauri, it's trillions of miles. So we come up with different units to make numbers more usable, or more, make them more usable or easier to deal with. So for example, the first one that you're going to be encountering is the astronomical unit, or AU. And that is simply the mean distance between the mean distance between the Earth and the sun. Said 149 million meters. And so when we talk about distances within the solar system, we often refer to those as astronomical units. If someone were to ask me, what is the distance to Pluto? I would tell you that Pluto is 40 AU away from the sun. So 40 times as far away from the sun as the Earth is. But even AU becomes rather cumbersome to use when we start talking about distances to stars. And so now we're going to be using the term light year. Now, light year, as it happens, is around 9.5 times 10 to the 15th meters. So it's 4 orders of magnitude larger than the AU. What a light year is specifically is the amount of distance covered by light within a year. As we'll learn later on, the speed of light is constant. And as we'll learn later on, nothing can travel faster than the speed of light. So the speed of light in a vacuum has a very specific velocity. And so it takes time for a light particle or a light wave to go from one point to the other. And so a light year is the amount of distance that a light wave travels over the course of a single year. Now, a parsec, and we'll go over what the meaning of a parsec later when we talk about parallax. But for right now, just know that a parsec is equal to 3.26 light years. While it may not seem, you may ask the question, you're talking about a factor of 3, why come up with a new unit? A parsec actually has a better physical meaning, as it were, a much more observationally based meaning than a light year. So astronomers tend to like it better. So one might ask, how did one originally get to the astronomical unit? How did humanity first measure that accurately? Was it because ancient Greek philosophers calculated distance using newly invented methods of geometry? NASA launched a probe to Earth that traveled all the way to the sun. So we're talking much later in terms of time. Einstein's theory of relativity predicted what the distance should be, or the distance was measured by careful observations of Venus as it transited the sun, or passed between the sun and the Earth. I'll give you a few moments. If you said D, you would be correct. And this was done, if memory serves, in the early 1800s. Could be off on that. But we're talking about late Renaissance period. So reasonably recent time frame. So for a very long time, the distance between the Earth and the sun was not known. It certainly wasn't known in the time of Copernicus or Kepler. And we'll talk about the implications of that later on. So it was through a geometric determination. The distance was determined geometrically during that event. So we now have much better ways of determining astronomical units, primarily, or measuring the astronomical unit, primarily through satellite, through the study of satellite, or through the use of satellites. Very small. So what do I mean by very small? What I mean is subatomic particles. The smallest particle that we're going to be talking about is a quark, which is something that makes up a nucleus of, or what makes up a proton. And when you're talking about a proton, you're talking about something that is 10 to the negative 15 meters. So a meter is roughly about that big. So we're talking about something that is 15 orders of magnitude, not 15 times, but 15 orders of magnitude smaller than this. So 1 order of magnitude smaller would be something like this, a centimeter. Yes. So now that would be, sorry, losing my mind. That would be 2 orders of magnitude. Sorry, the centimeter is 2 orders of magnitude. But hopefully you get the idea, is that the order, this is exceedingly small value, and quarks are even smaller than that. And then when we talk about the simplest atom, the hydrogen atom, we're talking about is an electron orbiting around a proton. Here we're talking about a order of magnitude that is 5 times larger, or 10 to the negative 10 is roughly the orbit of an electron. Incidentally, fun fact, the universe, while we experience the universe as solid, particularly around you, you experience the universe as solid. It's really not actually the case. If you were to say, take the distance between, if you took the sun and the earth and you looked at the distance between them, and you took a proton and an electron, took their sizes and looked at the distance between them, and sort of took the ratio of that, there is the space between an atom, or the space in an atom, the space between an electron and a proton, is far, far larger with respect to the sizes of the objects involved than for the Earth and the sun. So what that means is that the universe, as we see it, or experience it rather, is mostly empty, is mostly just void. And so it is only because of the fact that our eyes are of a certain size that we have, we perceive things as being solid. We literally just can't, we don't have the resolution, we don't have the ability to see things at such a small scale. And because of that, we see things as solid. But in actual fact, most everything is empty space. Talked about well, orders of magnitude. So again, a human is roughly around 1 to 2 meters high, or 10 to the 0th meters. Planets orbit stars around 10 to the 7th or 10 to the 8th, meaning we're talking about 7 to 8 orders of magnitude larger than you are, and it balloons out from there. And then even further, you get to galaxies, which are on the sizes of 10 to the 21 meters, or 21 orders of magnitude larger than the human. And then you get into larger things such as clusters and superclusters. Point being is, very quickly, as I said before, you get to sizes that are incomprehensible. There is no way for you to really understand or conceptualize what 10 to the 20th meters is. I don't even think we have a prefix for that. Also, we have time. The age of the universe is also inconceivable. The age of the Earth is, in my opinion, inconceivable. I'm going to be showing later on, we're going to be scaling things down in terms of time to illustrate just how short of a time humanity has been in the universe. The universe itself has an age of around 13.8 billion years. The Earth is around 4.4 or 4.5 billion years. And humanity has only been around for roughly 10,000 years or so. So when we talk about the universe, to talk about the universe, its evolution is another fine example of that range in spatial scales that I'm talking about, or range of order of magnitude, range of order of magnitudes that I was talking about. Because when we talk about the very beginnings of the universe, our understanding of physics only allows us to get down to 10 to the negative 43 seconds. And then very consequential things happen as the universe evolves over time scales of from 10 to the negative 43 to 10 to the negative 34, and so on and so on. So we're talking just blips of time. And then the blips become seconds, the seconds become minutes. Then you start talking about between essentially the time frames between relative important epochs, hundreds of thousands of years to millions of years to billions of years. So speaking of timing, getting things, of scaling things, I think it was Einstein who came up with the idea that, and sorry for all the notification dings, Einstein came up with the idea of scaling things down so that we really could have an understanding of just how short of time that the humanity has been here. Now, I think he did it originally on a calendar. So, but let's do it within 24 hours. So let's imagine that the universe is, as I said, the universe is 13.8 billion years old. Let's imagine scaling that down to 24 hours. So creation occurred at midnight. So at this point, the universe is hot. It's a dense bath of photons. Really only if it actually, you could say particles because at this scale, it pretty much is the same thing. 2 seconds later, hydrogen and helium form, the first baryonic particles, or the first atoms form. 2 seconds after the Big Bang. 10 minutes later, the first stars. So it took 2 seconds to make elements. Then it took 10 minutes to make stars. So a good fraction of the universe, you don't find anything but just elementary particles flying through space. And only hydrogen, helium, and a little bit of lithium. Then, if we're talking about in terms of us, the next really important epoch is when the solar system formed. And that forms roughly 16 hours later. So at 4 p.m. The first primitive life forms occur an hour and 20 minutes after that. So it took a really long time for life to form. And that actually has implications when we start talking about the search for extraterrestrial life. And then 4 hours later, and I really need to edit that, 4 hours later, it took the first primitive forms of life to become multicellular. So it took longer for single cell organisms to become multicellular than it took for those single cell organisms to form to begin with. Evolution is a really slow process. Then 2.5 hours later, or 2 hours later, you had the first dinosaurs appear. They only got to spend 20 minutes in the sun before, a rock came and wiped them all out. The first hominids appeared 7 minutes later. So now we're talking about 11 hours, 11:59:20 p.m. So 20 seconds after 11:59 p.m. That is when the first hominids were around. So we haven't been on this scale. We have not, or even our ancestors have not been around for a full minute. When we talk about the first modern humans, when we talk about those humans that we can predate back to having some form of, biologically, there's a definition for that. But for my purposes, a cohesive civilization at any point. We're talking about 11:59 p.m., 59.8 seconds. That is a blink of an eye. So we have been around in the scale of the universe. If you think about it in terms of a day, we have been around for approximately 0.2 seconds out of 24 hours. To me, that is significant in and upon its own right. The fact that all of us around us, everything that we know, all the history of what we know, occurred within that time frame. All right, for that, I'm going to stop, and I'm going to end this lecture. Hopefully you've found it enjoyable, and next time I will talk about the science, and I will talk about what is science and what is the scientific method. All right.